We are excited to transition to our robotics panel. The panel will be moderated by Scott Amyx, Managing Partner at Astor Perkins. Joining us on the panel are Peter Howard, CEO of Realtime Robotics, and Professor George Konidaris, CTO of Realtime Robotics. Please help me welcome our panelists.
All right. Thank you so much, David. I appreciate that. And welcome, Peter. Welcome, George. Good to speak with you again. For those of you that are joining, I'm sure they're very interested to know more. So if Peter and George, if you could introduce yourselves, but also introduce Real-Time Robotics, that would be great.
George, do you want to get started?
Great, sure. So hi, Scott. Thank you for the invitation. Hi, David. Nice to meet you. So my name is George Konidaris. I'm one of the co-founders of Real-Time Robotics. I am also a professor of computer science at Brown University. And one way to think about our company is that we build a control processor that goes between a robot of any type or any brand and the person that has to program that robot to be able to make it do interesting and cool things. And we've developed the first couple of layers of technology that provide basic physical intelligence that enables those robots to be easy to program, to be performant, and to be able to interact with the world in much more or much less structured environments than is typically the case. Peter, do you want to?
Yeah. So Peter Howard, co-founder and CEO, although I am the first non-technical of the founding team, the first business guy to enter the team. In terms of the focus of the company, George gave a good description of kind of what we do. In terms of a little bit higher level, why we do it. Basically, we are the company is very much focused on trying to reduce the cost, the time, the difficulty of setting up robotic systems, and also improving the throughput of those systems. Essentially, trying to change the ROI, the return on investment that users of robotic systems will experience in a way to enable them to be used in a much broader set of application areas.
So I want to leverage what you were just explaining, Peter, because I think this is a great starting point for the audience to understand. Is that when it comes to manufacturing, it's actually a very low margin business, and they really need to be able to maximize the physical assets that they have, factories, and of course the machinery. So help us understand, why is that hard for them currently outside of solutions like real-time robotics, and in the context of transitions, whether it's transition from internal combustion engines to electric vehicles, to the ability to actually be more dynamic in terms of meeting market demands and creating new products, either for new demands or for local markets and customization, for instance?
Well, so I think it's important to first understand that the robots are fairly narrowly applied in terms of automation tools today. Only about 2 million robots are currently operational. And that's largely because, as George likes to put it, robots are just dead stupid. They're a chunk of metal and kinematic strength that has zero intelligence. And the way robots are programmed, the way that they're employed today, is extremely time-consuming, tedious, inflexible, because they have no kind of physical or sensor intelligence built in. Robotic systems today, they say that the International Federation of Robotics says that the cost of ownership of a robotic system over its life is roughly $350,000. The cost of the robot itself is less than 10% of that. 75% of the cost is the programming cost, the reprogramming cost, the redeployment cost that any user is going to experience, because product life cycles are short and they do need to be redeployed. So in order for, there are very few things that robots aren't, with the right programming and peripherals, that they're not capable of doing. They're not affordable. They don't work economically. So by providing some basic kind of autonomous self-programming skills, if you will, for some of the most basic things, like how do I move from, how should the robot move from pose A to pose B to get some work done, without kind of removing the complexity of doing those basic things. Robotics is just too expensive for all but the most repeatable, long-lived type of applications out there. There's a field of companies, we're one of those, that is working on trying to apply certain basic intelligence. Ours is kind of the physical motor or motor sensory skills that would enable robots to be applied with say 70 to 80% less programming work. So this is our kind of keen focus.
So George, I want to ask you, because it's not just simply ease of programming, but I think both of you have mentioned the term throughput. Is when you think about a cell unit and the different robotic arms that are working together to accomplish a certain task, it's the pace at which they do it. So if they do it at a kind of slow, methodical, maybe they get that certain activities done within a certain amount of minute. But you guys are actually really pushing the envelope in terms of kind of the maximum throughput that can actually occur in the safest manner under this broader category of motion planning. If you could just kind of elaborate, that'd be helpful.
Sure, totally. So the way to think about the way that robots have been built or deployed so far, as Peter was saying, is that they really are just, at the moment, trajectory replay machines, where a human will program a trajectory. And when you replay a robot's trajectory over and over again, you can do that really quickly. And so, let's say that you're in a factory producing cars, you can churn out some large number of cars a minute, because you can act very, very quickly, because the robot has got no intelligence in it. It's just reproducing these motions in an open loop way. So the challenge for being able to make these robots more dynamic, more adaptable, much easier to program, is for them to be able to generate those motions on their own. But then there's two challenges. One is you need to do the computation to generate that motion, and that's the motion planning problem, which I'll define in a second. You need to be able to compute that motion very quickly, so quickly that it's essentially imperceptible. So there's no slowdown when the robot generates its own motion versus when it reproduces one from a human. And then the second problem is to be able to actually do the execution at the same speed as the robot's kind of underlying native controller would do it. And that's because throughput is king. So for the first problem that I talked about, having the robot generate its own motion, this is called robot motion planning. So the example I like to use is when you or I are opening a fridge and we're reaching in the fridge to pick up a beer. If you watch your arm the next time you do that, you'll notice that you take a highly specific motion that goes around all the sort of shelves in the fridge, all the other things that are in the fridge, doesn't knock into anything, and picks out the beer at just the right place. Your hand goes to just the right place for that to happen. Your elbow goes to just the right place that you don't bump into the fridge or knock into any of the shelves. And computing that plan is the motion planning problem, like finding that trajectory through space for your arm. And that was studied for decades before the breakthroughs that allowed our company to be launched kind of put that problem to bed finally. Does that make sense as a sort of analogy?
It is a very good analogy. I would add one of the other things that in order to achieve economic viability, which is a throughput problem and a cost problem, On the throughput side, there is also the ability to coordinate multiple robots. Because generally speaking, a given task, you're going to spend let's say $20,000 to $30,000 on the robot and end effector. You're likely to spend 3 times that amount on the material handling to get the object in and out of the workspace. And if you could double throughput by adding a second robot and triple throughput by adding a third robot, your cost per unit produced would fall significantly. But particularly for what George described as dynamic problems, where things aren't necessarily always in the same place and straightforwardly repeatable, coordinating multiple robots to be effective in a common workspace is a very challenging problem, and one that the type of imperceptibly fast motion planning basically kind of solves in a native sort of way. So we are able to add second and third robots to workspaces, thereby increasing throughput by only increasing the cost of the system by 10 or 20%.
So on that note, Peter, when we think about the context of warehouses, let's say, for example, Amazon warehouses, where you have these small warehouse robots that are constantly moving objects and goods so that it can be properly fulfilled quickly. Similarly, in a warehouse, you could have autonomous or semi-autonomous forklifts and other types of machinery that are all working in very kind of tight spaces. Can you talk about some of the challenges of this kind of dynamic environment that's not factory floor based, and challenges that gets created as a result, and the complexity of the modeling that needs to be in place to handle some of these things?
Sure. George, do you want to actually tackle the kind of difference between a high degree of freedom robot and a kind of the low degree of freedom cart robot?
Sure. So the thing about a robot that's essentially a kind of box on wheels, right, is that you can think of it as really operating in a 2D space where it's kind of operating on the flat plane of the ground, and really you can think of it as a box. And so when you're doing motion planning, you're really kind of coordinating the motion of multiple boxes through space. And when it is just boxes in roughly a 2D field, we can kind of do that in real time at the moment using a sort of normal software motion planner. Things get more complicated when, as you say, suddenly you have a forklift, when there are extra dimensions, and those dimensions really matter, or where you have a robot like an arm, which is let's say a 6 degree of freedom pose, and then the kind of kinematics of the arm are complicated, and that makes motion planning slow. So companies like Amazon don't need motion planning when they're coordinating even hundreds of box-like robots on a grid, because that collision detection or motion planning problem is relatively simple. But as soon as they put an arm on those robots, or they add a third dimension like height, suddenly the motion planning problem becomes complicated, and you need solutions like ours to be able to resolve it. And it's all about making sure the two robots are not in the same space and time. And obviously the problem grows as the number of robots involved gets larger.
And I want to go back to Peter. If you could talk about, for real-time robotics, what are the segments or verticals that you guys are well suited for?
So where traction found us originally is in the automotive space, which we had not thought would be very interested in our technology, because there are very well established ways of building cars with welding robots, for example. But it turned out that the value proposition for the time savings we generate, which is generally on the order of 80 to 85%, less programming time, less calendar time for doing model implementations or model changeovers, has generated enough of it's a compelling value proposition. And as we worked with different automakers on more flexible logistics-oriented applications, they kept saying, well, it's going to take, these are great. We really want to pursue these with you. But they're going to take 3 to 5 years minimum before we can get them through our processes and procedures to certify them safe. In the meantime, the basic motion planning capability that you offer could be saving us, hundreds of thousands of hours a year. And so we have kind of gotten swept up. Part of our activity has gotten swept up in the vortex of just resolving or solving the problem of programming, say 8 to 16 robot cells, robotic cells, in a much more cost-effective, much more time-effective way. So that's one category, and that turns out to be a multi-billion-dollar a year market, something very, very much worth focusing on, but does not have kind of the huge rapid growth potential that the market perceives, that companies in the space perceive for logistics and warehouse automation applications. And in the logistics and warehouse automation space, where we have come much more recently to find strong applications, the places where, let's say, system integrators have come to us for help is in terms of controlling, again, as I mentioned before, adding additional robots to complicated workspaces, where they can say multiply the throughput by 1.7, 1.8 for adding a second robot using our technology. Whereas if they were to try and use more traditional methods, they might get a 20% boost or something like that. So this is in applications such as palletizing, depalletizing, where by throwing additional robots at the problem, you can multiply the throughput for a pretty fixed overhead investment in material handling. The same is we're beginning to see opportunities on the parcel induction side. We're also beginning to see traction for sortation applications, where similarly use of multiple robots is helping change the ROI equation. Competing with humans is a very difficult thing.
Mm-hmm. Absolutely. And George, I want to go back to you to kind of talk about this programming, because I think we kind of glossed over, but there's a lot of sophistication. So for instance, prior to real-time robotics, if you were to program a cell unit with a number of robotic arms, the programmer would have to essentially figure out what was the optimum sequence of activities, and which arm does what, and in how and what kind of motion or direction, for instance. Your software is able to actually do quite a bit of planning and scenario and auto optimization. And I wonder how you're able to do that. If you could just, again, elaborate a little bit more.
Sure. So before we came along, what would typically happen in something like an automotive work cell is, let's say you'd build 4 robot arms into a work cell, which would require some mechanical engineering. You'd model that thing in CAD. You'd put down 4 robots, and then you'd have to specify at each time where you wanted each joint of the robot to be. So you'd say, well, this robot should take this trajectory through space, and you'd kind of program that trajectory by moving the robot and writing down the locations. And then you would sort of think about how the robots might clash into each other. And so you'd sort of have to conduct this whole thing like a sort of ballet where no one can see anyone else, right? Everyone is just replaying their trajectories blind so that they don't crash into each other. And then there was some safety you could add, like you could add a zone where the 2 robots should never be at the same time. And so that meant if there was any process variation, they would sort of correct by avoiding each other. This is an incredible amount of detail to provide for a single work cell, and it gets exponentially harder with the number of robots in the work cell. But of course, all of this is exactly the sort of thing that massively parallel compute is for, right? So what we've done is through a combination of sort of custom hardware and clever software and just really thinking hard about the fundamental problems, we're able to say, for each of those 4 robots, tell us where the business end of the robot should be. Point the weld gun or the paint gun needs to be over here and it needs to move in this direction. And we will take care of computing everything else for you on the fly in real time. And so what it means for the programmer is they just, they need to think about what their business case requires. Like, I need this, piece of the car painted from here to here. And they can forget about all the other details of the robot. We take all of that for them in just the same way that, you don't have to program your printer by reasoning about where the print head should go. That's crazy. Instead, you program your printer by, telling it what sort of image you would like it to produce, and the printer driver handles the rest. So one way to think about that is we're providing that level of abstraction leap, but for robots.
Yeah, I think I was just going to say this is so powerful because I think we're just starting to see some of the no code, low code on the SaaS side, but this is essentially what you're solving. And I wonder, again, you mentioned it a little bit before, but I mean, how much time savings are we talking about? So let's say for a 4-unit work cell, I mean, what's the savings?
300. So it will typically take a system integrator on the order of 400 hours, 380 to 400 hours to program that for robot work cell, and you can do it with our technology. Most of the work, by the way, in when using the real-time controller is going to be building the CAD model to begin with, which you can't really get around, but you're gonna be finished with that in about a week, so about 40 hours.
Amazing, absolutely amazing. Now, are you able to share any type of case study or customer that you could share publicly in terms of how you guys are applying some of these optimizations?
Yeah. So if you don't mind me grouping together, so we have been doing considerable amount of work with one of our original investors from our seed round, which is Toyota, but also including BMW, Audi, Volkswagen, Ford, etc., as well as some of the newer companies like Tesla and just getting started early contact with Rivian. But among those different, I'm not going to be specific about whose they are, but among those, one of the companies that is most advanced in bringing our technology not just to the design process but to the shop floor has seen 70% reduction in overall time that it takes to get a new model rolled out and up and running. Which is significant. It's normally a 16-week process, and if you can catch back 70% of that in terms of time savings, that this is line down time, that's a tremendous savings to you. In addition to the savings that are generated by fewer people working on it for a shorter period of time. In terms of, so that's an example of the shop floor. And by the way, it's quite similar in terms of building the digital twin in the engineering department. The savings are a little bit higher because the work is more specifically intellectual. But on the optimization side, so one of the things that we haven't mentioned is because it is so labor intensive to do a programming iteration. Typically, if you're setting up that 4-robot cell and you're going to spend 400 hours, you'll probably have time to do a second iteration where you check and see if you can get a little bit better cycle time than the first iteration. So if when using our technology, you can either manually iterate more quickly, or we're just coming to market at the beginning of next year with a reinforcement learning AI that will run hundreds of thousands to millions of iterations, looking to minimize that cycle time, kind of intelligently chasing improve local minima, and then hopping outside to try to find, chase another local minima. And there we're seeing cycle time reductions that range. This is cycle time repeatably. Kind of this. It's a savings for the life of the product, if you will. There we're seeing cycle time reductions of between 25 and 50 or 60%. So it's because the sorts of things with complex, high degree of freedom robots that do affect cycle time are not at all intuitive to our human brain. And you find things like shifting the base of one robot by 4 inches cuts the cycle time by 30%. Things that you would just, when you see it, you say, no way, that's not possible. But it's that sort of thing that the brute force reinforcement learning type of approach, and you can do that because of the speed of by which we're able to run those iterations. But you just see results that you would otherwise not expect.
So this is so highly relevant, and I think real time from a market timing, it couldn't be better, because again, every auto manufacturer is having to, they have to at this point comply and start to roll out electric vehicle portfolios. But it's not just the integrators, but it's also the components. All the OEMs, all the primes and tier ones, they have to supply new components, because again, fundamentally, combustion cars require entirely different set of components to support engines versus electric vehicles and batteries. So that means that everyone in the value chain is going to have to really pivot and reprogram just about everything. And I wonder the kind of size of opportunity that means for real-time robotics, but also some of the complexities and new challenges and new product enhancements that needs to be thought about as well.
Yeah, so it is, you're spot on, Scott, that the industry, stodgy old automotive industry has really woken up. And VW, for example, has a new CEO who is all about remaking everything about how they build cars. So it's not just the Teslas and the new companies coming in, but whole company cultures are being rebuilt right now. I would say the rebuilding of the culture is one set of problems. It's its own thing. But it represents tremendous opportunities for companies like ours who have product offerings which can be an important piece of that overall puzzle. Challenge for, as you point out, challenge for us and for others is that it also requires, most of these applications require a significant amount of deep thinking and set of kind of custom or focused improvements. And the key to doing this in an intelligent way requires that you've thought about the platform underneath, so that any new functionality that you build that may look specific actually turns out to be quite useful across the board. And therefore you need to have thought through the substructure of what you're doing in such a way that it supports all these different kind of micro requirements that may take you this way or that way.
And George, did you want to add to that?
No, I think Peter, what Peter said is exactly right. I think the opportunity is gargantuan, and you know, automation has been changing the world for centuries now. I think that is just going to keep going and make everything better, as long as we're willing to seize the opportunity and be bold.
Very exciting, and thank you so much. And I want to hand it back to David, who's going to close out this panel for us.
And I would like to thank our panelists again.